Welcome to Lesson 7, Action Potential. So what is an action potential? An action potential is a signal that is conducted by the axon of a neuron. It's an electrical signal that travels along the nerve cell, as you can see in this diagram here. Through this, neurons are able to communicate with each other and with our entire body. Now, before we go through the 5 main stages, let's first look at the important terminology. So, neurons have gated ion channels, which open or close in response to stimuli, which can result in changes in the membrane potential. There are also voltage-gated ion channels, which open and close in response to a shift in the voltage across the plasma membrane of a neuron. An increase in the magnitude of the membrane potential is called hyperpolarization. This occurs when the net diffusion of potassium ions out of the neuron increases and makes the inside of the membrane negative. On the other hand, a decrease in the magnitude of the membrane potential is called depolarization. It occurs when the sodium-gated channels open and increase the diffusion of the sodium ions inside the membrane, which makes the inside of the cell more positive. Now that you have a good understanding, let's look at the 5 main stages. So we have step 1, which is the neuron's resting state. At rest, a neuron has a negative charge inside. It's about negative 70 millivolts. This is due to the uneven ion distribution. There's more sodium ions outside and more potassium ions inside. The sodium-potassium pump maintains this state by moving ions against their concentration gradients. So after the resting state comes step 2. Step 2 is the threshold. Through a strong stimulus, the depolarization reaches a level called the threshold, which is at around negative 55 millivolts. You can see on the diagram over here. At this stage, many voltage-gated ion channels open, allowing the sodium ions to enter the membrane. Now comes step 3, called depolarization. It can also be called the rising phase. Here, there's a rapid Na plus influx, which makes the membrane positive. Because of this large change in the membrane voltage, it results with an action potential. On this diagram over here, you can see that the red line represents step 3. So now after the action potential itself comes step 4, the repolarization, or also called the falling phase. Here, a negative membrane potential is restored by the inactivation of sodium channels and by the opening of multiple voltage-gated potassium channels, which increases the outflow of the potassium ions. Now comes step 5. The sodium channels now close, but the potassium channels stay open longer than needed. This causes the neuron to become extra negative as too many potassium ions leave the cell. Here in the graph, you can see the yellow line represents this process. Once the potassium channel closes, it returns to its resting state. This whole process is followed by a refractory period, which is when a second action potential cannot be immediately triggered. After a while, the cycle continues again. So now let's take a look at the conduction of multiple action potentials. In other words, a series of action potentials. The action potential is initiated at the axon hillock. So this is a part of the the neuron. And it propagates along the axon. The sodium ions flow inward to depolarize a region, which triggers depolarization in its neighboring regions. The potassium ion flow outward to repolarize the previous region. The refractory period ensures that the signal moves in one direction. This process allows rapid transmission of nerve signals across the neuron. So the main takeaway here is the directionality of the signal. As you can see, it does not happen backwards at all. It happens in one single direction. That's it for this video. Thank you for watching.